So we're going to start with a Ferris wheel problem because I feel like that's a fairly straightforward way to go. We need something that spins. So here's a Ferris wheel. And, Ferris wheels in the fair, they're really simple to construct. They're easy to operate, which is why you see so many of them at state fairs. There's a lot of variety on the Ferris wheel too. You've seen probably the ones where they have like the cage and you're inside a cage and you can hold your cage and keep it from spinning so you can be upside down, blah, blah. There's a lot of variety at state fairs because it's relatively safe. And although they can be operated in an unsafe manner, they are consistent operators and people tend to pay to be on them. So that's why we see so many Ferris wheels. Let's set the size of the Ferris wheel to be relatively small. We'll say 10 meters across is the radius. And I'm going to give you some specifics. You'll need to decide which information I'm giving you. You know it's a kinematics problem because that was the lead into this conversation. So if you are paying attention yesterday, you understand that a kinematics problem is likely to have this kind of information presented. Correct? But obviously I'm going to obfuscate it as much as possible. I'm going to make it complicated or confusing or try and hide the information. Obfuscate. I can't spell it, but it probably starts with an O. What's that? Yeah. You probably would. Let's see. Obfuscate. I don't know. Is that it? Is it? Obfuscate? I don't know. You said you were going to spell check it. Did you spell check me? F? It's obfuscate? All right. Well. Fun enough. So here's the details. I'm going to say the problem twice. I'll speak slowly. In this Ferris wheel, the ride takes 1.5 rotations to get to full speed from rest. In this ride, the Ferris wheel takes 1.5 rotations to get to full speed from rest. At full speed, a person at the top of the Ferris wheel has an apparent weight that is half of their actual weight. At full speed, a person riding the Ferris wheel will feel half their weight when they are at the top of this ride. Their apparent weight will be half of their weight. What is the maximum speed of the Ferris wheel? What is the angular acceleration experienced by the Ferris wheel in radians per second squared while accelerating? And how long does it take to get to full speed? I'm asking for these 3 pieces of information. Okay. Now, I don't know if you have the skill set to do this problem, but you've been given all the pieces to do this problem. So whether you have the skill set or not, it's been presented in this class. There is nothing additional that you would need to do this problem. I would encourage you to consider that some of the information I have given you is specifically about centripetal acceleration. That should be clear, but it might not be. The next thing I will tell you is that apparent weight refers to the normal force on you. You can't experience weight, but what you feel is the normal force supporting your body. Your apparent weight is the normal force. You're supposed to know that. If you didn't, put it in a box, highlight it, study it. But again, you have all the information you need to do this problem. Whether you can or not remains to be seen. So I'm going to encourage you to start someplace. Consider the person when they're at this point in the ride. We'll assume the ride is spinning in such a way that when they make it up there, they experience a certain normal force. Get started. I'm going to call. All right. 3 groups have successfully recognized that there is a centripetal motion problem that has to be solved. That you only have 2 pieces of given information, 1.5 rotations and 0, and you will need another way to get more information. They successfully pieced together that when you're at the very top, you're experiencing 2 forces, weight downwards and normal force upwards. The net force has to be equal to MAC because you're traveling in circular motion. If you did not know to start here, that's a problem for you, but it's a circular motion problem. All the clues were there. And I suggested forces be involved by naming the normal force as one of the values you were given. So you've got to look for these clues. Now, right now, if you want to do well on your next test and on the AP exam, off to the side where you are struggling, you should put a little box and say, the best way is to look at the clues that were given. This was a circular problem and a force was named. That likely makes it centripetal motion. That's the kind of thing you need to study to help you identify. The problem isn't going to just scream at you, this is a centripetal motion problem. So those were the clues. By the way, you're also supposed to know that there's more than one way to calculate centripetal acceleration. You might pick one that is more aligned with what you need. All right, carry on. If you've been doing everything fine and you plugged in as we said, you should have 0.707 radians per second as omega. If you don't know how to get there, you should raise your hand right now. All right. I'm going to go over it, but you need to hear this. If you just write down what I write down, you're wasting your time. Okay? I said that you should probably deal with the net force problem because that's what's been clued in. Forces were indicated, and we're traveling in a circle. They have to be unbalanced at the top, or else you don't travel in the circular path. That's why I drew it this way. They're unbalanced at the top. You're also supposed to make the positive direction towards the center of curvature. So I'm making downwards positive. Any question about that choice? You were given a piece of information in the problem that the normal force was half of your weight. Good so far? So subtract and get 1/2 mg equals MAC. So I can cancel out the m's. Now, if you want to start putting in values, which people did, you should probably pick out which version of centripetal acceleration you want to use. And I want the angular speed of the roller coaster. I don't need the linear speed of the person. Yeah.
How did you just get rid of the mg?
I didn't get rid of it. I subtracted. Okay. If I factor out the mg, I get 1 minus 1/2. I have 1 mg minus 1/2 an mg, leaves me with 1/2 an mg. It's okay. Yeah.
So you have the centripetal formula, like with the v squared over r. Why is the next one w squared times r instead of divided by r?
All right. I have a question I think is pertinent to the room. And although it has been explained, it was explained kind of in a footnote last semester. So tangential velocity equals omega times r. Correct? So we did talk about this a little bit, but not in great detail. So if I would prefer to have this in terms of the angular speed, I can substitute here, meaning I can place this here. When I do, that gives me omega times r squared over r. The result of doing this is omega squared r squared divided by r, or omega squared times r. So, although I put all of it on there, this is just two different ways of calculating centripetal acceleration. This way is for when you have the velocity of a single object as it rounds a corner. This way, if you want to know what the acceleration required to be on a platform or an object that is rotating. This is the speed of the entire platform as it rotates. This is just the speed of the person as they travel along the top of the merry-go-round. I'm interested in something about the merry-go-round, not something about the person, which is why I chose to find omega. Now, that being said, cancel the m's and substitute. And I've discovered that I have another problem. And so let's handle this other problem. We have a value. We can get a number here because we know that g is 10 meters per second squared and the radius is 10 meters. So just looking at that, 1/2 times 10 meters per second squared equals omega squared times 10 meters. We're looking for omega, but pay attention to the units. If I do the math here, I'm going to get 0.5 on the left, right? Half of 10 is 5. 5 divided by 10 is 0.5. But I am dividing by 10 meters. When I divide both sides by 10 meters, the meters part cancels, which leaves me in per second squared. If you know you are solving for an angular quantity and the units cancel, that means you're in radians, because radians is a unitless quantity when referred to things that are spinning. My understanding is that your knowledge of radians is lacking. So I'll take the square root here, which is going to give me the 0.707 radians per second. But as I want you guys to be learned people, I recognize you don't know why radians are unitless. And although that makes me confused as to how it was explained to you, I'm going to do my best to explain it. But I found in third period you guys didn't do something that I expected. Did you guys prove the size of pi when you were in like elementary school? I know. For I am sad. When do you think you learned that circumference equals 2 pi times the radius? It's an elementary school topic, but sometimes students don't get to it till middle school, depending on where they went to school. Now, I don't know where you learned this. It might have been middle school. That person should have immediately had you figure out what 2 pi is or what pi is. Either one would have worked. It's not hard to do. But do you first understand that this also is delta x equals delta theta times r for one circle, right? If I say you're going to go around once, this would be circumference. Does everybody understand that? Because if you do, it'll make what we're about to do easier. If I wanted you to figure out what pi is, I would have you bring something that's a circle to school. And I would tell every kid in my elementary school class, my 5th grade class, go home and bring something that is circular to school that's small enough to fit at your desk. Luckily, you guys are so scared of being dehydrated that most of you have something in front of you right now that you could use. Bigger will work a little bit better, but here's how you do it. You take whatever that is, your water bottle, in the old days, coffee can, but I would bring out things that are circular. Take whatever that is and tie a string around it. All right, just tie a string around it. Then you pull the string off, cut it, and measure the length of the string. That's circumference. Then, using a meter stick, measure the diameter and cut it in half. That's radius. If you take the circumference and divide by the radius, you'll get 2 pi, the number of radians in a circle. But the units have to be part of this. You wouldn't measure circumference in meters and radius in feet, right? You measure them in the same units, which means you're going to get something that is meters divided by meters, or centimeters divided by centimeters. This is how you have children figure out what pi is, and you have them do it all over the room so they all find out it's the same number. It's built into the structure of nature, this relationship. And if you don't understand the implications of that, then you probably need to mature a little bit about what a true fundamental constant of nature is. There's not very many of them. G is not a fundamental constant of nature. Neither is most of the fundamental constants you've learned. Fundamental constants like this one and the natural log E, these are part of the fabric of nature. They exist in any unit, in any measurement, devoid of something that humans have created. Pi is a part of the nature of the universe in a way that's not particularly easy to understand. But when you think about all the things in nature that are circular and know that this ratio is kind of special, you begin to have maybe an understanding of its usefulness. But we define this to be radians, a way of measuring the distance around a circle that's based on its exact measurements of circumference and radius. Now, I don't mean this to be rude, but you guys don't have a good appreciation for any number that is in radians. So please, in your head, just remember 6 radians makes a circle, right? 2 pi is 6.28. 6 radians makes a circle. So when you're comparing numbers and looking for things, know that when you do your conversions, keep that in your head. Because over here, we are probably going to have to convert that 1.5 rotations to radians. And I know it should be around 9. Because 1.5 times 6 is 9. But you'll screw up the conversion and not think twice about it because you don't have a sense of size. A circle is 6 radians. 1 rotation is 6 radians. Get it into your head that way. It will help. Okay. So we have moved to a new place in this problem. I'm assuming that now that we've done the first semester physics part, the stuff we talked about yesterday, you should have no difficulty doing. It's a motion equation calculation, and as long as you ensured you were in the same units, you should have no trouble. I should be able to pick on 2 tables in the next 60 seconds. Bowser's Castle. You can give me either one of them. I don't care which one.
The acceleration is 0.028.
Can you tell me how you got 0.028? And I assume you mean radians per second squared. How did you come to that conclusion?
Because we use the formula 2 alpha delta theta equals omega squared minus omega not squared.
Excellent. That's what I would have done. I think that's enough explanation. Does anybody need it worked out more than that? You would have had to convert this to radians successfully. What do you get when you convert that to radians? 9 point? Thank you. Anybody need to see that done? Okay. So we're all okay with that? Hogsmeade, can you guys tell me what you got for time? Can you tell me how you did it?
I used the equation delta theta equals 1/2 omega plus omega initial.
Excellent. I think that'll work just fine. Does anybody need to see that explained in more depth? All right, so the kinematics part isn't the hard part. It's all the stuff around it. The going from one unit to the next, knowing which unit's appropriate to use, stuff like that. Agreed? I think we should probably practice one more before I add new things. Yeah?
Could you just quickly go over how you converted the rotations to radians?
Sure. 1.5 rotations. Doesn't have anything in the denominator, so I'll just put 1 in the denominator, but there's no unit there. It's okay. You are not the only one. So then I choose my regular conversion theory, which is to use unit multipliers. I have rotations in the numerator, so I'll put rotations in the denominator, and I want to be left in radians. I know my conversion fact is 1 rotation is 2 pi radians. The rotations cancel. That's going to leave me a 1 in the denominator of my answer because there's nothing with units there. And I'll get my 2 pi times 1.5, which gives me 9.42 radians. All good? So if you have a number that you have to convert and there's nothing in the denominator, just put a 1 in the denominator. It takes 10 seconds for the ride to get to full speed, and that full speed is traveling at 1/4 rotation per second. It starts from rest. I would like to know the angular displacement of the ride, the angular acceleration of the ride in radians per second squared, and I would like the centripetal acceleration experienced by the child when it's at full speed. We've only got 3 minutes. So did you figure this out to be 1.57 radians per second? All right. Did you do your unit conversion correctly? Does anybody need help doing that? Okay. Once I knew that, I could immediately find the centripetal acceleration because it's just omega squared times r. So 1.57 squared times 3. Now, the rest are just motion equations. And not particularly interesting things to do there. Just pick one and solve for it. Does anybody need me to show you how I chose to do it? All right, so work these out. I will post the answers to your homework before I leave here today. The homework was just sent out as an announcement because it was just the first page. There are 8 exercises. You should practice. Tonight is Wednesday. If you're needing help with